Yeah, so I'm Daniel. I'm with Fraunhofer Focus in Berlin. And I'm going to present like a joint work. So I'm going to talk about implementing low latency, fast startup, and switching for low latency, low delay LCD dash. Hard title, but we're going to digest this later on. So this, as I said, is a joint work. So I also want to mention Alex, Khalid, Min, and Stefan. And Alex and Khalid are actually also here, so you can come find us if you have any questions. And by the way, the clock is not running. I'm happy about that because I have too many slides, but maybe you want to start. Okay, so I want to start with what is LCD dash, and we're going to do that the old-fashioned way. So we're not going to ask an AI. We're going to actually check the specification first. And if we search for LCD in the 6th edition of the MPEG dash specification, we actually get 5 hits, but they're all on the same page. And I marked the relevant part here in the red box. These are only representation IDs. So that doesn't help that much. So if you want to understand what LCD dash is, we need to ask someone. So we ask is Alex here, human LLM? So you can ask Alex pretty much everything. Yeah, so LCD dash is short for low latency, low delay dash. The work originally started in SCTE. And essentially it enables multiple new features that are combined in the 6th edition to form LCD dash. So it allows us to start playback with very low delay, and we're going to see examples later on. Also play with very low latencies, that's what we want to achieve usually. We had a panel on this. And also ABR switching at partial segment boundaries. And then there are some additional LCD benefits, like it's really compatible with HLS, at least segment-wise. It allows us to efficiently fast forward. We can use bootstrap representations and get like every nth partial segment and use that for fast forwarding. It solves something that I have been struggling with, Ali has been struggling with, a lot of people have been struggling with. Piers also mentioned this. So throughput calculation for chunk transfer encoding, that's a tough problem for clients because you basically get the segments over time and the download time will correspond to the duration of the segment, so your classic throughput calculation will not work anymore. So the idea behind LCD dash is also to solve this with partial segments. And then we can make use of the standard templating mechanism that we know from Dash. Okay, one of the core concepts, and I'm going to show you an example in the MPD on the next slide, is the concept of partial segments. So the idea is that we divide a full segment into multiple partial segments. These are corresponding to CMUF chunks. And each partial segment then starts or can start with an IDR frame, but most importantly is individually addressable. And you see an example here on the right side of the slide. So on the top you see a full segment representation. These are the segments that we know. In this case it's around 2 seconds, one full segment with an IDR at the beginning. And then we have a partial segment representation where actually the full segment is divided into 4 partial segments, each of them starting with an IDR frame. So we can individually address them and we can immediately start playing one of these partial segments. It enables low latency playback, as I said, by downloading partial segments once they are available, and it also enables low delay playback if we select one of these partial segments from a bootstrap representation. I have examples coming up in the use case section. So for those of you who like reading MPDs, so these are some of the attributes that we need to add to the MPD to support LCD dash. There's the concept of subnumbers now to individually address the partial segments. This is what's marked in the purple box. And then we also need to signal the number of partial segments. So we have this K attribute now on segment timeline level, can also be specified on segment template level, that basically tells us how many partial segments are included in a full segment. So in this case, it's 4 for each of the full segments. And we also need to signal the frame type at the start of the partial segment. So we have this new segment sequence properties attribute or element with an SAP type corresponding to the IDR frame in this case, and the cadence. And the cadence is the important attribute because that tells us what the IDR cadence is for the partial segments. In this case, we have an example with 4, which means every 4th partial segment has an IDR frame. And on the bottom one, you see a bootstrap representation where we actually have a cadence of 1, which means that every partial segment has an IDR at the beginning. And then you also see this essential property. So that's the way to tell the client that it needs to support segment sequence representations. And basically, if a client is not supporting that, it will filter out the corresponding representation or adaptation set. Okay, some of the LCD use cases. So first of all, low latency playback. So as I said, we had a panel about this. We talked a bit about chunk transfer encoding. This is a new concept, or at least the technique behind this is a bit different. So on the top, you see a normal representation without partial segments. And assume that we are at the now time. This is the dotted line at the right side. So as a client, I would need to wait for full segment number 2 to be available before I can download that and play that. I need complete move MNAT box combinations. So in this case, I would need to start playback with full segment number 1 somewhere, and then I have a higher latency if you compare that to the bootstrap representation on the bottom. Because in this case, I can immediately start downloading partial segment number 1 from full segment 2, and partial segment number 2 from full segment number 2. So those are the ones that are marked in green on the right side. So in this case, I can start with lower latencies simply because I can address parts of the full segment much earlier than I could with a full segment. And there's also the concept of low delay startup, and I depicted the clean switch scenario here. There's also the dirty switch, which we cannot cover here today. But basically, we have bootstrap representations. Those are representations with partial segments and an IDR at the beginning of each partial segment. And that way, we can immediately select one of these partial segments at startup. Hopefully, we can decode that pretty fast because we have an IDR at the beginning. And then after startup, we would switch to either full segment representation or a partial segment representation where we have only an IDR at the beginning of each full segment or at the first partial segment of a full segment. So the idea here is really that we can decode that faster because we have an IDR more or less at the time that we join the stream. Okay, so these are the main concepts, and then we did some tests and we implemented support for this as well. So this is the test setup that we have, and we had a panel with people from ATEM here. Mikael was on the panel. So we have a reference content provided by the ATEM encoder and by the packager. There's also support in JPEG, as I learned today from Dennis, and also the LiveSim 2 now supports LCD. That was a contribution by Qualabs. So there's a lot of playground now or content to play with. So that's the server side, the content side, and then we have support for LCD Dash in Dash.js. So that has been supported now since 5.1. I added that and we did the release, I think, a few weeks ago. And on top of that, so playback at Dash.js, content coming from ATEM. We also have a small analytics platform that we implemented with a metrics server, an SQL database saving the metrics, and the metrics library collecting certain metrics on the client side. And the way we did that is not using CMCD in this case. We wanted full control over how we do the reporting. And I also actually added some hard-coded values or some hard-coded measurements in Dash.js itself. So that gave me the maximum flexibility to actually derive the metrics that are important for the analysis. Okay, so for the testing, we actually had a very simple test content. One test content, which we called normal non-low latency content. Full segment duration was around 2 seconds. One representation with 4 Mbit and full segments with an IDR at the beginning. And then we had LCD dash content, again, same segment size, but 4 partial segments per full segment, leading to this 0.48 seconds. And a bootstrap representation for the startup with partial segments and an IDR at the beginning, and normal representations with only the first partial segment with an IDR. So from a player's perspective, I would start playback for the LCD dash content from the bootstrap representation and then try to immediately switch up to the normal representation. So these are some early results. So the first thing we tested is the low latency playback. And in this case, what you can see here is on the x-axis, the timestamp of the content, and on the y-axis, the value in seconds. And in yellow, you see the live latency, and in blue, you see the buffer level. And this is the measurement for the low latency LCD dash content. So what you can see here is that we aimed for a latency of 1.5 seconds. This is the latency from the encoder to the player. And the playback was quite smooth because we can actually request these partial segments. We can build up a reliable buffer. We did not run into an empty buffer. And something that we also talked about in the panel, we slightly adjusted the playback rate to get to this 1.5 seconds. So that was a 4% decrease or increase of the playback rate. So overall, this was quite smooth. And then we tried to actually do a playback with 2-second latency for the main content with segment durations of 2 seconds. And there's a typo on the slide. It should be saying approximately 1 segment duration. And in this case, we ran into problems, as you can see. So the buffer level was oscillating. We can see that the live delay is increasing and trying to decrease again and then increasing again. So you have these steps in the live delay chart. And this is pretty, I mean, that's pretty obvious because we try to aim for a 2-second latency with 2-second segments. So that does not give the player enough time to download and build a reliable media buffer. If we increase the latency slightly to 4 seconds, to basically 2-segment durations, then we see the same pattern as we saw with LCD dash content. So that's pretty reliable. But obviously, in this case, we have a higher latency compared to the LCD dash content. And we also checked or tried to estimate what the low delay or what the fast decoding actually gives us in terms of the startup. So I need to explain this a bit. So you see the stacked bar chart here on the left side of each of the parts of the figures. So what I try to do here is actually figure out how much or how long does the player take to decode the segment. And I try to do that by kind of accumulating the manifest download time, the manifest parsing time, the init segment download time, and the time it takes to download the first segment. So you add all of these up, and then you compare that to the media start delay. So basically the time the player takes from instruction to playback to rendering the first frame. And if you take both of these or these measurements and you subtract one from the other, then you end up with the light, what we call it, light green part, which is the decoding time. So that's actually the difference between the media start delay and everything that happened before. And we did this for 2 different devices, a macOS Chrome and also a Samsung device that comes up on the next slide. And in this chart, you can see that the LCD dash content had a better startup delay. So the startup time was lower, but it's not really coming from the decoding time. Because if you compare these 2 light green parts, they're pretty identical. The main difference here is the download time for the worst media segment. And this is obvious. Because we have a partial segment, which is much smaller, we can download that much faster compared to the full segment. So in this case, yes, the player was starting up faster with LCD dash, but it was not coming from the decoding because probably the platform is decoding in faster than real time. The same pattern is true for the Samsung device. The values are higher now. So the media start delay, especially for the non-low latency stream, was around 2 seconds, which is quite long. But as you can see in the light blue part of the chart, the first media segment download time was significantly higher for the Samsung TV compared to the LCD dash content. So again, comparing the light green parts here, not much difference, but the difference comes really from the fact that the download time of the first segment was longer. All right, conclusion. So what we saw is that LCD dash enables low latency streaming using CMUF chunks, individually addressable partial segments. We also saw that LCD dash has the potential to improve the startup time, but according from our test at least, and we want to do additional tests with high bitrate content, different platforms, that was not coming from fast decoding, but from the obvious speed improvements caused by smaller segment download times for the partial segments. Next steps, we want to evaluate the throughput calculation. This is the thing that I mentioned in the beginning. So probably we see benefits here compared to a CMUF chunked low latency streaming with chunk transfer encoding. And we also want to run additional tests in a controlled environment. So we have an ABR test bed. We want to run that against different trajectories and see how well the content performs. And then there are some challenges on the client side that I need to work on the dash tail specific side. And very important, the SVTA is also working on guidelines so that whenever we want to check a specification, we actually find something about LCD dash. So the dash IF working group is taking care of this. Okay, final slide. So that was all I had, but I also want to invite you to Berlin to come to our Media Web Symposium in June. We will have a face-to-face for the Dash developers, Dash.js developers there, and lots of interesting discussion tutorials and also talks. And I think I'm perfect in time because they started the counter too late. So I have 7 seconds. Thank you.
I got it here. Yeah, quick question. So for the case where you have the partial segment also have studied with IDR. So I'm just curious, how would that compare with you actually have your segment length to be 0.48 seconds?
So you mean you have like full segments, and do you want to call them full segments with 0.48?
Yeah.
Essentially, that's the same. So, I mean, and I had a discussion with Thomas Stockhammer about if we want to call that partial segment or not. I spare you the details, but yeah,
Yeah.
But essentially, it's the same concept, but we don't have the mechanism to really signal the different IDR structures in the segments without these partial segments. We could do that. So in theory, you're right. A full segment could also be like a shorter.
Yeah. But of course, this L3D stuff still has some, because you don't have to start with IDR.
Correct. Yeah.
When you start with IDR, it's the same. Then.
Yes.
Okay.
My question was almost same. So.
Tasso?
Yeah, thanks for the talk and the work that you put into this. When you did the measurement for the decode time, until which frame did you actually decode?
I measured when the first frame is actually rendered. So I checked the loaded data event, the HTML5 event. So when that was triggered, and there was another thing, I have to check this again, so I compared this, but I basically took this event and the timestamp from starting the playback, and that's the difference more or less between that.
But were you targeting a specific frame, or in other words... Like,
at the playback start, you mean?
At the playback
no,
start.
that was pretty random, but I run like 200 samples to make sure that we not always start at the beginning of the frame, but rather like a specific live edge, which corresponds maybe to the middle of the frame, to the end of the segment, and yeah.
Okay, maybe because this is very interesting, because I did similar tests,
Yeah.
and for me, when I was targeting specifically the end of a long segment, let's say 2 seconds or 4 segments, the difference was obviously massive. Like on my MacBook, this takes like 300, 400 milliseconds to no-op decode.
Okay, then maybe that's what was causing the results as well. So I can maybe force it to start at the end of the segment to make the times higher, yes.
Yeah.
So that was randomized, yeah.
You have a question? Yes, sir.
Yeah, real quick. I see that you got the latency down to 1.5. Do you think similar techniques will keep compressing it down, and is that kind of the roadmap of this, or do you still need to switch to a different protocol ultimately? Yeah.
When is the mock session coming up? So I think mock will still give you lower latencies, and as I said, that was really the encoding, so the latency from the encoder to the actual playback. But I think we can achieve latencies around, let's say, 1.5 seconds with Dash, but if you want to go lower, I think you need something else, to be honest.
Yeah, I
Yeah.
have a very small question. It's been a while since I looked into this, but is there a way to have like tiered like length segments, like going from 1 second to 2 seconds and 4 seconds cadence?
You
Is
mean
the spec covers that, or is it only one?
you can have different representations with different cadences, yes.
Okay.
Do you mean in the same representation later on switching to a different cadence? I don't think that's supported, but you can have different cadences for the different representations, yes.
Okay. Okay, got it.
All right. Thanks, Daniel.
Thanks.